Okay, so here's our second last lesson on our stoichiometry unit, and we have done most of the heavy lifting already. So as a quick review before I do this, if you guys can solve the type of question that looks like this, I give you a certain amount. I don't know what the amount is. It could be in liters, it could be in grams, it could be in I can't think of anything else, maybe moles, something like that. I give you a certain amount. Then the next thing you're going to do is you're going to take some sort of ratio. I don't know what the ratio is going to be, but a good idea might be it might be something like moles per liter, because that would cancel your liters here. Or it could be a mole per gram, because that'll cancel your grams here. Something along those lines. Then the next thing you do is you use another ratio, and this would be like a 2 to 1 ratio based on your equation. Doesn't have to be 2 to 1, but something like that. And then when you're finished, you use some sort of other ratio, and now in this case you're doing something else, like you're looking for something like, say, liters over mole, like you might do 24.8 liters per mole, or you might do grams per mole, you might do something like that. Okay. If you get that process, you've got stoic down. Okay, that's like the main focal point of our unit. I've only got to show you basically two more things. One of them is a scientific technique called a titration. Okay. And if any of you guys end up going on to university level chemistry, you're going to do titrations. This is a really common sort of technique to do. Basically, the idea is that it's a quantitative analysis tool. Quantitative meaning that we're looking for a quantity. And typically we're looking for either one of two things. We're either trying to figure out the concentration of an unknown sample, or sometimes we can also use it to find the mass of a sample. But most of the time, and what we're going to do in our class, is we're going to do it to try to find the concentration of an unknown sample. Let me give you an example of a real-world application where this would matter. Any of you guys have well water? Like you live on a farm? Anybody ever had testing done on it to figure out, or just like regularly done to make sure that it's still safe to drink? Okay, in a way, maybe it should happen, but in a way that's kind of a titration, because what they're going to do is they're going to try to find the concentration of different ions. For example, whether the iron ions are too high or too low, whether the sodium or chlorine ions are too high or too low for it to be safe drinking water. Okay? And what they're trying to do is they're trying to calculate the concentration. And if the iron ions, say, were above a certain concentration threshold, then perhaps it might not be safe drinking water. Does that make sense? And so we can do this in a lot of different ways. In our lab, what we're going to do is we are going to do a titration on just basic household vinegar, like you'd buy in the kitchen. Okay. In our lab, if you go buy a bottle of vinegar in the, what did I say? Buy in the kitchen. Buy to use in the kitchen. Okay, you get what I'm saying. If you were to look at a bottle of household vinegar, it's probably going to say something like this: 5% weight over volume. Next time you see vinegar, take a look. It's going to list a concentration. That's how much mass there is of vinegar in the solution. And what we're going to do is we're going to test and see whether that's actually true. Okay? Many household products will give you a concentration amount and say, well, this is how much there is. Here's another example. My daughter's toothpaste has fluorine in it, because that's supposed to help protect against your teeth, right? Well, it's going to list its concentration and say that there's 30 parts per million of fluorine in it. You know what I'm saying here? Lots of things are measured in concentrations. Alcohol, for example. Beer is bought at like 5%, or wine is 7%, right? Long story short, a titration is a technique you would then use to check and make sure that whatever concentration it's supposed to be, we're checking to make sure that that's actually true. Does that make sense? Normally, when we want to figure out a concentration, to find that concentration, we would know it because we made it ourselves. In our first unit, if I asked you, how do we know that the concentration is blank moles per liter, hopefully the answer is, well, you made it. Right? You weighed it out on a scale. You found the mass of a solute. You found the volume of solvent, and you calculated it. But this is more of a quality control check. A titration is then a method to say, well, here's a solution that somebody else made. They, air quotes here, said it was 5%. Are they lying? Does that make sense? So that's what we're going to do, is we're going to test and make sure that the concentration of our unknown sample is actually what it says it happens to be. So let me show you today kind of in notes how to do this. And I gotta be honest, if it doesn't fully make sense based on me like putting words and pictures to it, I think it's gonna make a lot more sense after we actually do our lab on Wednesday, Thursday. Does that make sense? So bear with me if you feel like you don't fully get the concept, because this is really a doing technique. This isn't really just listen to me talk about it. You actually have to try it once. So I'm gonna fast forward, if you guys don't mind, to a video that I have somewhere right here. I have a movie. I found a little animated GIF here that's gonna try to explain how titration works, and I'll let it run through a few times, and then we'll talk through, and then I'll go back to the other notes. So the first thing you need to do is you need to put a sample inside your burette. And I already showed you guys how to use this burette. And so what you're going to do is you're going to put a certain amount of acid in the burette, and you're also going to put some inside the flask down there in the bottom. Okay. You're going to add 3 drops of indicator. The most common one we use is phenolphthalein. And the reason why we use phenolphthalein is because it has a very distinct color change. Phenolphthalein, if you guys know it all, goes from clear to pink. What you're going to end up doing is, once you've measured the initial amount in the bottom of your flask, which I hopefully have done, and then the initial amount in the top of the burette, you're going to add it little by little. And what's going to happen is it's going to turn pink. And I think I showed you guys this briefly. What happens is, as it's turning pink, is the base is getting touched to the indicator. And as base touches the indicator, it will turn pink. But it'll immediately neutralize. And when it neutralizes, then it turns back to clear. Well, eventually it will reach a point, we call this the end point, where it no longer turns clear anymore, and it will stay pink like that, which then means that all of the acid in the bottom of your flask has finally run out. And what you're hoping for is just a very faint pink solution. So let me try it one more time from the top here. Start by putting, start by filling some acid in the top of your burette, and record the initial amount. What they've done now is, now there's some acid sitting in the bottom of the flask. Okay. You're going to put 3 drops of indicator in the bottom of the flask, and when you do that, acid and indicator is clear. So that's why this is still clear. Now there's a limited amount of acid in the bottom of that flask. In the second burette here, they've put a base. And what they're going to do is they're going to add some base little by little, and hopefully we'll see that it turns pink. But see how they swirled it? The pink goes away. The reason why is that the acid in the flask neutralized the base, and so although it temporarily turned pink, it neutralized it back to a pH of 7. Well, eventually you're going to run out of acid in that flask. The acid that's in the flask is your limiting reactant, and eventually it will run out. What we're hoping to do is figure out the exact drop using that burette reading there, where all of a sudden it does not turn clear anymore. And that must be the exact amount required to neutralize. We call that the end point. Eventually you'll have a flask that's very faintly pink. You want the one that's on the right, not on the left. And that's kind of how the technique works. Does that make sense at all? I think I briefly showed you one of these as well. We'll do it again on Wednesday. Let me go through my notes starting from here. Here's basically the concept. We are going to put a known volume, typically of acid, in the bottom of the flask here. How are we going to know its volume? Because we put it there. We're going to use a measuring tool. In that video they showed you there, they use the burette. We're probably going to use a pipette, just because a pipette's a little bit easier to work with. But we could use a burette. But we're going to put a known volume of acid right here, and it is going to be the limiting. It is going to limit us down here, because once we put our prescribed amount of acid down here, we're not adding any more. So it's usually 5 or 10 or 25 milliliters down here. We're also going to add a little bit of phenolphthalein. Do you guys have your data booklets nearby? Find your data booklet and find the indicator phenolphthalein. What pH range does phenolphthalein change color from? Yeah, it's 8.2 for pH to 10. And I believe the way it works is that on the 8.2 side, it's clear or colorless. And on the 10 side, it's pink. I have that correct? So here's what that means. If you have acid down here in this flask and you add phenolphthalein to it, what sort of pH would an acid be? Above 7, below 7? Yeah, well below 7, right? So if there's acid down here and there's phenolphthalein, it should be on the clear side of the color change. You get what I'm saying here? Which is why it starts off clear. Now, in the top, in the burette, you're going to put a known volume of a base. But not only are you going to know this volume, you're also going to know its volume and you're going to know its concentration. I'll show you in a second why you need to know its concentration as well. But we're going to know the volume and the concentration of a base up here. And this is going to be what's going to be excess. Because what ends up happening is I can keep adding more and more base out of this burette if I want to. Let's say I run out of base in the burette. Just refill it. Does that make sense? So this is going to be always what's excess. The acid in the bottom is going to be limited because once you have a certain amount in this flask right here, you never add more. Okay, so you got some base in this flask. You tip the little stopper to allow some to go in, and it turns pink. Why does it turn pink? Because a base, in the presence of phenolphthalein, a base would turn pink. But the pink disappears right away. It's going to turn pink briefly, and then it's going to dissipate. Why does the pink go away? Well, although the base just touched phenolphthalein, which makes it pink, the base is also now reacting with your acid. What happens when a base reacts with an acid? Neutralizes. Creates a pH of, let's say, 7. Well, although the pH was briefly increased to about 10, it's going to immediately neutralize right back to about 7, which is why it'll immediately turn clear again. Does that make sense? So you're going to see it go pink, clear, right? So what's going to end up happening, though, is you're going to eventually reach a spot where when you add your acid, as the acid gets dropped in, it's going to stay pink. The reason why it's going to stay pink is that limited amount of acid that you put in the bottom, however much quantity it was, eventually all of it will be neutralized. And so then there won't be any acid left to make it go pink and then return back clear again, and it's going to stay pink. And what we're hoping to find here with very, very precise measuring tools, because this burette right here can measure to basically the nearest drop of liquid. We're hoping to find the exact drop, and thereby the exact volume, where it gets neutralized. And we call that the end point. So I'm going to put a little, actually it's right here, perfect. We call that the end point. And this is when you are done. By done, I mean don't add any more volume of base because this is exactly neutralized. That may actually be a little unfair. It's not exactly neutralized. It's exactly neutralized plus 1 drop. Does that make sense? Because that 1 drop extra is the drop that made it stay pink. But minus the fact that you're 1 drop too far, this is when we're finished. Now, when you do this technique, then you're going to have 3 measurements. You're going to have a volume of acid that you put in the bottom down here. You're going to have a volume of base which you used, and you're also going to have the concentration of the base which you titrated with. And using that, that's enough information to know how concentrated the solution of acid was you started at the bottom. Okay. And so I'll show you guys the math on how this works, and hopefully the math makes sense because it's not any different than what we've been doing before. When I was showing you guys something like this, right here, the math is like the exact same as we've always been doing. Your biggest struggle with this is going to be to try to figure out what numbers go where. That's all. So, this would be considered picture-wise a good endpoint where it's basically just barely pink, or hopefully you're only 1 drop over the equivalence point. What we did in our lab, you guys remember the lab we did last week where we were trying to do a filtration? I asked you guys to kind of use that burette and add some solution little by little. Remember how it turned white? Does that make sense? But at some point, I just told you, like, dump a whole bunch in just to make sure that all reacts. We don't want to do that today. We don't want to keep adding more and more of this liquid until it becomes deep pink, because then we've gone way too far and we've added too much volume. We want to literally find just the moment where it's like just faint pink. Now, one more thing that we'll do in titrations, the standard way of doing things is you don't do something once. Okay? Good science doesn't mean you just test something once and you call it a day. Most of the time, though, in our class, like any of the labs we do, I mostly just have you do something once and that's all we have time for. Does that make sense? Like we did 1 filtration. We did 1 gas collection when we calculated the value of R. But ideally, we should do it multiple times. So as a way to try to be more accurate, as a way to have a reliable result and increase your accuracy, you want to do this a number of times. So the standard requirement in a lab is this. You want to get 3 results within zero point 0.2 milliliters of each other. That's kind of the standard requirement. 3 results within zero point 0.2 milliliters of each other. What that means is if the first time that I try to titrate something, it takes 15 milliliters for it to turn pink, and then the next time it takes 19 milliliters to turn pink, that's not very good because that wasn't within 0.2 milliliters of each other. Whatever volume you add right here, like from here to here, however much volume it requires for it to turn pink, we want to do this 3 times and have it be super consistent. Okay. When I was in university, I took a chemistry class where we had our mark was not based. You know how like on your labs here, if your guys' lab is not successful, I don't deduct marks because you have a poor lab, like percentage wise. You know what I'm saying? Like if you have a percent difference of 100%, I don't deduct. Right? Well, this university lab, that was the only place your mark was given. It literally was the professor or the lab instructor would give us a sample. They would know what its concentration was, and they would say you calculate it. And based on how close you were, that was your grade. So like if the right answer was supposed to be 10 moles per liter, and I said 15 moles per liter, I would fail. Makes sense? If you said 10 moles per liter and I said 10.3 moles per liter, I might get an A minus. If you said 10 moles per liter and I also said 10 moles per liter, then you know what I'm saying here? That was what Mark was based on. So I remember for this lab, what we would do is we were allowed to go into class an hour beforehand and set up, and we would wash all of our materials. We would make sure there was no reason for there to be an error due to impurities. We'd wash everything, we'd dry everything, we'd have everything set up, and then we were given a 3-hour time limit. And we would do as many trials as we could in that 3 hours, with the idea being that if we have lots of data points, hopefully we'd be able to be very consistent. And so like if I got not just 3 trials that were close, but if I had, say, 17 trials that were all exactly the same volume every time, wouldn't you feel very comfortable with that? You know what I'm saying? But if I had like 1 trial, if I only had time to do 1, would you feel comfortable that your grade was going to be resting on that 1 trial you did? Well, no, probably not, right? But if you could find a way to be very efficient with your time and you could just do trial after trial after trial after trial, and let's say the first time you got 15, the next time you got 14, the next time you got 14 again, the next time you got 14 again, the next time you got 14 again, would you start to feel pretty comfortable with your work? Does that make sense? Anyways, the point I have here is that when you guys do this, though, the 3 results within 0.2 is considered to be the base standard for a high school lab. That's good enough to say we're pretty close. So. Okay, I showed you the movie. Why don't we try some examples here? So, in order to try to set the scene for what's happening here, I'm going to draw pictures of just a basic titration setup. And like I said, if this still doesn't fully make sense, please don't stress. I think it'll help more once we actually do a titration on Wednesday. So this is meant to be a burette right here. The burette is that very, very fine measuring tool where there's all these markings along the side. If you guys remember, the precision of a burette was to the nearest 1/10 of a milliliter. The precision of a burette is to the nearest 1/10 of a milliliter. It is one of the most precise measuring tools we have for it to be able to handle that. And what we're going to do is we're going to put in this burette right here, we are going to put in some sodium hydroxide. We put base in that burette. In a flask in the bottom, usually an Erlenmeyer flask just because they work quite nicely, we are going to put in a small sample, and the sample is going to be of nitric acid, HNO3. So that's kind of the stage here. We're going to put sodium hydroxide up here, we're going to put HNO3 down here. And we have to record how much HNO3 we put down here. So it says we put in 50 milliliters of this stuff down here. So we used a measuring device, and we know that we have 50 milliliters sitting down here of acid. They're also going to put in 3 drops of phenolphthalein. If it doesn't say that, it's kind of assumed we use phenolphthalein. It's the best indicator to use. What happens when you put 3 drops of phenolphthalein in an acid? What color will it be? Clear, yeah. So you won't notice anything. And then what you're going to do is you're going to start turning on the stopper. So you're going to rotate the stopper, and you're going to start adding drop by drop some of the liquid right here. Again, what happens when the base then touches the phenolphthalein? Turns pink. But this solution won't stay pink originally. Why not? Well, because although the base is going to touch the phenolphthalein and turn pink, it's also going to touch the acid and neutralize. And so it's going to go pink clear. Does that make sense? And so we're going to keep adding this liquid until eventually it stays pink. And the volume of the sodium hydroxide might have started here, but eventually it's going to be down here when you're done, because you will have used this much liquid by pouring it into the bottom here. And the drop in which it stays pink, we call that the end point. It's where, it's the point where you are going to end. Makes all the sense in the world, right? And by calling it the end point, though, we also mean that it's also sometimes known as the equivalence point. And the reason why we call it an equivalence point is that the amount of acid that you have down here that you limited with should be equal to the amount of base that you started with. And that's how you know to stop, because rather than the color disappearing, the color will just stay very, very faint pink. So that's kind of the setup here. Now our question is, can we calculate the concentration of this HNO3? So although we know the volume, what we don't know is the moles per liter. So we're going to try to calculate its concentration, because that's the whole point, is to figure out how much actually was there. Now for the base right here, I know how much volume I used though. The reason why I know how much volume I used is because I know where it started, I know where it finished, and the difference between those two there was 65 milliliters. And I can see that up here in the top here. It said 65 milliliters of titrant is used. If I didn't mention that already, if you guys don't know, the word titrant is used to describe whatever goes in this burette right here. That's called a titrant. Last thing, we also need to know the concentration of our sodium hydroxide. And so we know that it was that many moles per liter. You know why we know how concentrated it was? Because we made it ourselves. Right? How do you know the concentration of something? There's two ways. One, you either make it yourself. If you make it from scratch, you know how concentrated it is because you controlled how much volume and how much solute you had. But the other way that you can calculate concentration is what we're doing right here. We don't know the concentration of this unknown amount right here, but through this math process, now we can figure it out. So now it's time for the math. Let's start with what we what we do know. We know that we needed 65 milliliters of sodium hydroxide. And I know that the concentration of that sodium hydroxide was 0.4. Actually, I need more room here. Hang on. Sit down here. 65 milliliters of sodium hydroxide. And I know the concentration of it was 0.4. That was 0.400 moles per liter. That was its concentration. Next up, I don't really want to know about sodium hydroxide, so I'm going to put it on the bottom. Because really the whole point of this is I want to find that unknown concentration of nitric acid. And then the last step I've got, this one, maybe I've shown some of you this before, maybe not. We need to, units-wise, when we're finished, end up with moles per liter. That's our whole goal. We want to end with moles per liter. The way I'm going to do this then is I'm going to divide by 1 over 50 milliliters, which is a little bit different in terms of how we structure it, but watch what happens with our units now. This milliliters right here is going to cancel that milliliters right there. You guys see that? The first milliliters I started with, I'm actually not going to use it to cancel this guy right here. I'm going to use it to cancel the very, very last one. The sodium hydroxide is going to cancel right here. And the only units left that I haven't canceled then are moles and liters, because literally both of these units right here are still standing. There is one more thing I need to figure out, though. I didn't actually ever figure out the relationship between nitric acid and sodium hydroxide, so I should write a quick balanced equation. If you take NaOH and add it to HNO3, what kind of reaction takes place? Double replacement, or you could even call it neutralization, because neutralization always involves making water and some sort of ionic salt. The cool thing about a lot of these ones here is that it's almost always, it's not always, but almost always a nice 1-to-1 ratio. So we need ones here. So if you can follow along with what I did here, I started with a amount of base and a concentration of that base. Then I canceled out the base and converted it to acid. And then I like to do 1 divided by 50 milliliters because this is the constant, this was the amount of acid we used. Then this milliliters cancels this milliliters, and the only things left that I haven't canceled are moles per liter from right here and the nitric acid right here, which is my whole goal. I wanted to find concentration of nitric acid. So I just need my calculator now. So 65 milliliters times by 0.4 moles per liter times by 1 divided by 1 times by 1. That's all silly. Divide by 50. 0.52. So I got 0. Oh, that's not the right writing utensil. Where do I find the pencil again? There you go. 0.52 moles per liter of HNO3. Now we've calculated the concentration of our unknown solution. And like I said, there's actually a lot of practical purposes for this in life. If you wanted to double check and make sure that I tell you this is 5%, but you want to make sure, was it actually 5%? You know, if I tell you that there were 3 parts per million of iron in your water supply, this is a good way to double check it. You do what's called a titration. Okay, that was one example. How do you guys feel? Did I do an okay job of kind of explaining the first one? Because it's very rinse, lather, repeat. Like it's the exact same thing over and over again, just with like slight tweaks to it. So let's try another one. You have an unknown concentration of H2SO4. So again, if you feel the need to draw out the scenario just so you kind of understand what's happening, you're going to take your burette. This is your burette. Stopper. And in terms of this guy right here, we've got 75 milliliters put down here. We are going to then pour in, so this was your H2SO4 by the way. We're going to pour in some calcium hydroxide, and the amount of calcium hydroxide that we used here is 57 milliliters. From wherever we started to wherever we finished, the difference there is 57 milliliters. And then the last piece of information we need to know is the concentration of the calcium hydroxide was 0.25 moles per liter. How would we know the volume of acid in the bottom here? How do we know that it's 75 milliliters? Yeah, I mean, it sounds kind of silly to say, but we measured it and put it there, right? We used a measuring tool, and we put it down here. How are we going to know that 57 milliliters of calcium hydroxide is used? Well, because that's how much volume it's going to take from the top to the bottom for this thing down here to turn pink. How are we going to know for sure that this was 0.250 moles per liter of calcium hydroxide? We're going to make it. Yeah, we're going to make it from scratch. We're going to calculate a mass. We're going to put it into one of those volumetric flasks. So this is going to involve a little bit of overlap from one of our first units, but we're going to make this ourselves. Assuming then that all 3 of these numbers are true, then there's only 2 more things I have left to do. Step 1, I do need a balanced equation. 9 times out of 10 in acid-base reactions, it's probably a 1-to-1 ratio or a 1-to-2 ratio. But you just need to double check. So I'm going to take H2SO4. I'm going to react it with calcium hydroxide. And like any neutralization reaction, it's going to make water and a salt. This one does require a coefficient to be balanced, but I believe it's only on the water. So we now have enough information to start. I'm going to start with 75 milliliters of H2SO4. I'm going to multiply by, ooh, that's not right at all. Why should I not start with the H2SO4? Good, some of you get this already, because we don't know its concentration. So I shouldn't start with the thing that I don't know about. I should start with the thing that I do know about. So let's start with the 57 milliliters of calcium hydroxide. We'll times by its concentration, which seems a little bit strange because these things actually won't cancel. That one's in milliliters, that one's in liters, but that's okay. Because then I'm going to put my calcium hydroxide down here. I'll put my H2SO4 up here, 1-to-1 ratios. And I like to just write 1 divided by the 75 milliliters. Really, I'm just writing the reciprocal. And the whole reason for that is how now I can visualize that this milliliters and that one cancels, and this calcium hydroxide and that one cancels, and I've got everything I need now. So 57 times by a quarter and divide by 75 gets us 0.19 moles per liter from right here of H2SO4 from right there. Does that make sense? Okay, I've got 3 additional practice questions here, but if it's okay with you guys, as I look out over you, most of you seem to be looking like you get this. So why don't I just leave those for your own personal practice? If you feel like you want more practice on this, here's some more. I got a couple last slides here. All of this, however, hinges on one big thing. I'm going to go back to a previous picture I drew here. This volume right here. You know how in all of your labs I make you talk about accuracy and precision? I want to focus on accuracy right now. How are we going to know this number right here is accurate, this 57 milliliters? Well, I'm going to know it's accurate because I have a lot of faith that this tube right here, this burette, has been calibrated properly. And so when it says that each of these markings on the side here is 1/10 of a milliliter, as long as it wasn't calibrated incorrectly, I believe I should be able to trust that burette. Does that make sense? And in terms of trust, this 75 milliliters down here, I'm also going to trust that because, again, I believe that I'm going to be able to accurately measure a volume as long as the tools I use are not like incorrectly labeled and incorrectly calibrated. They're probably fine. But the whole thing hinges on this right here. This value right here, this concentration. If it is not accurate, if it's not 0.250 moles per liter, if it was 0.251 moles per liter, well, then the whole thing falls apart. And so the phrase I want to use here, it's called standardizing your titrant. I mentioned earlier, your titrant is the thing that goes in this tube right here. We have to know that its concentration is correct. It can't be about 0.250 milliliters. It has to be exactly. Like, we have to be certain of it. So I'm just going to read off my slides. I rarely do this, but I think this is probably the best for this section here. Oh, hang on. Sherry's here with food. Let's start with that. I see muffins and yogurt and bananas. Cheese strings? No cheese strings. Thanks, guys.
Thank you.
Okay, let me read off my slide here, which I rarely do. Before you do any titration, though, a titrant must be prepared accurately. That's that word again, accurately. You have to know with confidence the concentration of the stuff that you're pouring in through your burette. Okay. Now, one of the problems we have is that many chemicals can't be used because they're either impure, the impurities become part of the reaction, or maybe the chemicals absorb water, and therefore your concentration cannot be accurately determined. So what we have to use is something called a primary standard. And I cannot remember whether this is terminology I used in our first unit. Did we use the word primary standard before? Okay. So let's talk about these 2 words. You guys know the word primary from other places, right? Like the word primary means it's like the first something, right? If you're the primary something, you're number 1, right? A primary standard means that it is the original source, okay? When you standardize something, it means this is like the starting point that you're starting with. Okay, and what I mean is that it needs to be prepared, and it cannot be a liquid or a gas. Okay, gases can escape. Unless you have the world's best closed system, chances are a gas can escape. Why would we not want to create something out of a liquid? What can happen to liquids? Yeah, they evaporate, and that would change their concentrations. Long story short is that we have to make this using something that is a solid. We are going to start with a solid amount of primary standard, and that is going to be the basis upon which we make our solution. So if you guys recall from our first unit, what we're then going to do is we're going to take that flask, that's the volumetric flask. It looks something like this guy right here, and there was just one marking on it right here. And what we're going to do is we're going to take a solid, we are going to weigh the mass of that solid. And we should be able to weigh its mass very accurately because we have a scale that we know is correct. We're then going to put that solid inside the container. We are then going to add water. We're going to fill water directly up to the line, and this is going to be us making a solution from scratch. There's one more thing you have to do, though. Once you make the solution, you have to put a cap on the solution. Why do you have to put a cap on the solution? So it doesn't evaporate, yeah. Because if we just left it open to the air, then the liquid would evaporate. And you know how concentration is moles per liter? It's moles of solute per volume of solvent. If you were to allow your solvent, your water, to evaporate, it would actually cause your concentration to increase. In general, solutions increase in concentration over time. Let me say that one more time. In general, solutions increase in concentration over time because as water evaporates, there's less solvent. If there's a lower amount of solvent on the bottom, it actually increases your concentration. That makes sense? So, long story short, we have to make a primary standard. This is like a fresh, new batch that gets made every single time you do a titration. You never use like a solution that's like 3 days old because its concentration could have slightly changed in that time, and that loses us accuracy. Make sense? So the term we use is we call it standardizing a titrant. Standardizing a standard solution. I know we use this vocabulary. A standard solution from our first unit is a solution where you know its concentration. You know it accurately. You are confident in it. So, and anyways, that's the term, standardizing a solution. So basically the idea is you got to make a primary standard, and then what you do is you use this to calculate the concentration of something else. And that's more or less what I write in this set of notes right here. Sometimes what you actually have to do in a very, very complicated set of titrations, we're not going to do it here, but sometimes you use a primary standard, a solid, to make a solution. So you make a solution, which we then call a primary standard. Then you use that primary standard and you use it down here, and you do a titration with a base. And then based on that, then you know the concentration of the base. And then what you use is you use that base a second time, and you use that base to then titrate something else. And that gets kind of complicated. It's almost like a two-step process. You make a solution. You use that solution down here to find the concentration of your base. And then once you know the concentration of your base, you reuse the same base right here, only you then titrate something else that you want to find. And so sometimes there's a very long, convoluted process. We're not actually going to do that in Chem 20. I will show you how to do it in Chem 30, though. But that's kind of the idea, is that you always have to start, though, with a rock solid, no pun intended, starting point of a primary standard. And so that's the phrase standardizing a solution. Okay, I think that was my last set of notes, wasn't it? Okay. You guys have any questions? I've always felt like this set of notes here, although you can do the work on paper, it's going to make more sense hopefully on Wednesday and Thursday. So we'll do the titration on Wednesday, Thursday, but hopefully now you guys actually should be able to finish off almost all of your assignment. That assignment was only 7 questions long, but it should be able to be completed. I should show you one more thing though. On your assignment, I believe one of the questions is going to give you a table, and it might look something like this. It might give you your initial volume, and it might give you your final volume. I'm just going to make up some numbers here. If you ever get a table like this, if your initial volume was, say, 10 milliliters, and then your final volume was 8 milliliters, and then your initial volume was 8 milliliters, and then your final volume was 6 milliliters, and then 6 milliliters gave 5 milliliters, 5 gave 3, and 3 gave 1. Okay. If I give you a table like this, this is in your burette, that long thin tube. This is the starting and finishing values. And so what you really need then is to calculate the difference between the two. If you started with 10 and ended with 8, the difference is going to be 2 milliliters. Does that make sense? And if you start with 8 and end with 6, the difference is also 2 milliliters. And this would be 2 milliliters, and this would be 2 milliliters. But if you start with 6 and end with 5, the difference would be 1 milliliter. Okay. Sometimes when we do trials, we have to not use trials because they have to be within, if you guys remember, we have to have 3 trials within 0.2 milliliters of each other. And so this one right here is kind of like the outlier. We wouldn't consider it when calculating the volume. So if you ever get a chart that looks like this, you need to subtract the initial and final volumes to calculate the difference. And then the remaining ones that you can count, what we do is we average them. Okay. So if they were all 2 milliliters, that's awesome. But you only average trials that are within 0.2 milliliters of each other. So I believe that's the first question on the back side of your assignment. There's one that's got a grid that looks like that. So you got to keep going then until you get 3 that are consistent. So like that's actually the worst part of a lab is like let's say that you get your difference and one of them is 10.5 and then another one is 10.9 and another one is 11.2 and another one is 12.1 and like none of them are within 2.2 milliliters of each other, then you're not very accurate and you should keep going until you start getting a consistent value. So sometimes when kids do titrations with me, sometimes they only require 3 or 4 trials to get 3 consistent ones. I've had some groups, though, where for whatever reason, they had to do like 10 trials. And after they finally finished 10 trials, then they finally had 3 that were consistent. You know, like I said, in my lab, though, when I was in university, when my grade depended on it, I didn't just want 3, right? Like I wanted 10 consistent trials before I was willing to say, okay, I feel comfortable putting my grade on the line for this. So anyways, maybe some of you guys will get there at some point in your university labs if you go there. It was a fun course. I enjoyed it, but it was stressful because for the first time your mark was based on how good you were in the lab, not just that like you did the lab and talked about what happened. Okay, I think I'm done. You guys are good on questions? Okay, so work on either the lab from last week or your assignment, and I'll try to get those new labs posted online in the next day here so you guys can print those off. Okay, cool.